3. I/ATLAS, the improbability engine, the moment we couldn't see, October 29, 2025, 7:47 a.m. Eastern Time. The most critical moment in the history of interstellar astronomy passed in total darkness. At that exact second, 3 I/ATLAS reached perihelion, its closest approach to the Sun, just 1.4 astronomical units out, bathed in 770 watts per square meter of solar fury. If it was a natural comet, held together by ice and gravity, it should have fragmented spectacularly, shedding dust, gas, and secrets into the void. But Earth saw nothing. The Sun stood between us and truth, a cosmic sensor, blinding humanity at the precise instant when 3 I/ATLAS was most vulnerable, or most revealing. In Cambridge, Avi Loeb stared at a blank star chart and felt the weight of cosmic irony. "We calculated its path to the minute," he wrote in his Medium blog. "Yet the universe denied us the one observation that could settle the debate forever. And the timing wasn't just bad, it was suspicious." Of all the days in the year, perihelion occurred when 3 I/ATLAS was directly behind the Sun, invisible to every telescope on Earth, every radar array, every satellite. A 0.005% probability for a natural object. But for something that knew our orbital mechanics, it was the perfect cover. Loeb didn't sleep that night. He ran the numbers again, the 8 anomalies, the probabilities, the cumulative odds. Less than 1 in 10 quadrillion. In science, that's not coincidence. It's evidence. The 8 impossibilities. Loeb called it the improbability cascade. Each anomaly alone could be dismissed as a fluke, but together they formed a chain of logic so tight it strangled natural explanation. Anomaly 1, the alignment. 3 I/ATLAS arrived just 5 degrees off the ecliptic plane, the flat disk where all planets orbit. For an object from random interstellar space, the chance? 0.2%. "It's as if it studied our solar system before arrival," Loeb said. "Natural objects don't know the ecliptic." Anomaly 2, the sunward jet. In July, it fired a jet toward the Sun, not away. Comets can't do that. Solar radiation pressure forbids it. Yet 3 I/ATLAS did. "This isn't outgassing," Loeb insisted. "It's thrust." Anomaly 3, mass and speed. At 5 kilometers wide, it's 1 million times more massive than Oumuamua, yet it moves faster. In interstellar space, big things are slow. This one defies gravity's rules. Probability, 0.1%. Anomaly 4, the perfect route. It passed close to Mars, Venus, and Jupiter, then vanished behind the Sun at perihelion. A sequence so precise, so convenient for planetary observation yet Earth-blind, that the odds are 0.005%. "It didn't drift," Loeb said. "It navigated." Anomaly 5, industrial chemistry. "Its coma has more nickel than iron, like stainless steel, not stardust. And nickel cyanide levels orders of magnitude higher than any comet." "This is refined material," Loeb declared, "not random cosmic debris." Anomaly 6, the dry comets are 80 to 90% water ice. 3 I/ATLAS is 96% dry. "It's not a snowball," Loeb said. "It's a hull." Anomaly 7, the mirror surface. Extreme negative polarization, light reflecting straight back, like a lens or polished metal. No natural comet has ever done this. "It's designed to control light," he concluded. Anomaly 8, the WOW, echo. It came from the exact direction of the 1977 WOW signal, within 0.6% of the sky. "Two mysteries," Loeb said. "Now one. Multiply the probabilities, 0.002 times 0.001, times 0.00005 times 0.01 times 0.006 equals less than 10 to the power of minus 16.1 in 10 quadrillion. In court, that's beyond reasonable doubt. In science, it's a verdict. The radar that never fired the cruelest twist? We could have seen it. Loeb's team calculated that if Earth had been on the opposite side of its orbit, as it was 6 months ago, or will be in 6 months, 3 I/ATLAS would have passed just 54 million kilometers from us. Close enough for Goldstone radar, close enough to image its shape in 3D, close enough to see surface details, rotation, structure. But fate, or design, placed us on the wrong side. Now, even at its closest approach on December 19th, it will be 269 million kilometers away, too distant for radar. We missed our only chance to know for sure, Loeb told Congresswoman Anna Paulina Luna in a private briefing. Unless it reveals itself. And so, the world waits. Radio telescopes from Arecibo to FAST scan the sky for narrowband signals. Infrared arrays hunt for excess heat, a sign of internal power. Optical networks watch for artificial lights, a beacon in the dark. If 3 I/ATLAS is natural, perihelion may have shattered it, creating a dust cloud that will glow for weeks. If it's technological, it may release probes, it may transmit, it may turn on its lights. And when it reappears on December 19th, humanity will finally see what happened behind the sun. But Loeb already knows. The math doesn't lie, he told his team. Something built this. And it's not here by accident. The only question left is, what does it want us to see next? The silent listeners. November 1st, 2025. Arecibo, Puerto Rico. Virtual array. The world's radio telescopes didn't sleep. From the Allen Telescope Array in California to FAST in China, from Meerkat in South Africa to the upgraded dishes of the Deep Space Network, every major observatory trained its ears on the patch of sky where 3 I/ATLAS would reemerge. They weren't listening for noise. They were listening for pattern. Avi Loeb had issued a global call. Search for narrowband signals, artificial modulation, repetition, anything that cannot be explained by plasma turbulence or cosmic rays. For 72 hours after perihelion, silence ruled. Then, on November 3rd at 14:22 UTC, the Green Bank telescope detected a whisper, not a voice, not a message. A 17-minute gap in the background static. For exactly 1,020 seconds, the cosmic microwave background dropped by 0.0003%, a dip so precise it matched the duration of 3 I/ATLAS's rotation period. It's not emitting, said Dr. Kavita Ralph, lead analyst. It's absorbing, like it's using the CMB as a backlight, and something on its surface is blocking it in rhythm. Loeb's team ran simulations. The only explanation, a structured surface. Panels, vents, or apertures, rotating into alignment with Earth every 17 minutes, briefly shielding the CMB. Natural comets don't have rotating shields, but probes do. The finding wasn't proof, but it was consistent. And in the language of the improbability engine, consistency was the first step toward certainty. The heat that shouldn't be. November 7th, 2025. L2, Lagrange point. The James Webb Space Telescope wasn't designed to spy on interstellar objects, but as 3 I/ATLAS drifted out of solar conjunction, JWST's MIRI instrument captured something that made calibration engineers double-check their logs. At one point, 8 astronomical units, the object was cooling, as expected. But its thermal curve wasn't smooth. Every 6 hours it spiked, a 0.4 Kelvin rise, tiny but statistically significant, peaking in sync with its rotation, not from solar heating, not from outgassing, from internal energy. "This isn't radiogenic decay," said Dr. Lena Marovich, JWST's thermal lead. "That would be constant. This is pulsed. Like a battery cycling, Loeb's interpretation was stark. It's managing power, conserving it, using it in bursts. That's not geology. That's engineering worse. The heat wasn't radiating evenly. MIRI's spatial resolution showed it concentrated at 2 points along the object's axis, like engine nacelles on a spacecraft. NASA issued a cautious statement: anomalous thermal behavior under review. But in classified channels, the Planetary Defense Office updated its threat matrix. If 3I/ATLAS could generate internal heat, it could maneuver after December 19th. It could choose where to go next. And with its trajectory already aligned to pass near Jupiter in March 2026, the gas giant's gravity well could slingshot it anywhere. Earth, the asteroid belt, or back into interstellar space. The question wasn't if it was artificial. It was what it planned to do next.